In this experiment, we will explore an acid-base titration. As we do each week, we will emphasize aspects of lab safety and continue wearing appropriate PPE while working in the lab. We will explore how chemists experimentally determine concentration of a solution by performing a titration. We're also going to learn how to write a conclusion sections, making this our first full lab report. In a titration, we need at least two solutions. One is the analyte. This substance has an unknown value, such as concentration, that we need to determine. The other is a standard. We know the concentration of that solution. Raymond Chang offers a great definition for a titration: the gradual addition of a solution of accurately known concentration to another solution of unknown concentration until the chemical reaction between the two solutions is complete. Now, this is a very long way of saying we have a known and an unknown, and we're going to add one slowly to the other. When we perform a titration, we use a burette to add one solution to the other. This picture shows how to set up a burette for use. When you dispense liquid from a burette, you are able to accurately and precisely determine the exact volume that's dispensed. Generally, your known or standard solution will go into the burette, while your unknown or analyte solution will go into a flask or a beaker beneath the burette. You will need to use a burette clamp to hold the burette as well as a ring stand to support it. There's a more detailed video on the correct use of a burette located up on Canvas. Please review this video for details on how to use a burette. One of the main things that makes a burette different from other types of glassware is that the volume is measured from the top to the bottom. If you look at the image on the left, I've zoomed in a bit to the top of the burette. You can see that there is a meniscus in the fluid. That's that curved line. And then there's a dotted line that shows the bottom of the meniscus. This is where we'll determine the volume from. When looking at the volume markings on the burette, we can see that it starts at 0 and goes in 1 milliliter increments down to 5 in this image. It's then divided into tenths with a longer line in the middle indicating a half milliliter. We can then estimate one additional decimal place beyond those markings. So looking at where our meniscus is, we're between 2 and 3 milliliters. We are just barely past the half mil mark, but it looks like we're not quite to the 6/10 mark. So we need to estimate between the half mil and the 6/10, and we're going to estimate that's roughly 8. It looks like it's about 2.58 milliliters on the burette reading. It's always assumed that the last digit is an estimate. It's okay if it's not exact. This just indicates that it's more than 0.5, but less than 0.6. This is the initial volume of the burette before any liquid is dispensed. Notice how it does not have to be at 0 milliliters to take your initial volume reading. That's okay. On the right side, I've gone ahead and dispensed some of the liquid, and this is what the burette looks like. This will be the final volume. If we look at this, we see that we're between 21 and 22. This time, it looks like it's not as close to the 0.6 milliliter mark as it was in the first diagram. So I'm going to record the value as 21.56 milliliters. Remember that the second decimal place is an estimate of how far it is between the markings on the glassware. To calculate the volume dispensed then, we're going to just take the final volume reading minus the initial volume reading. And when I calculate those, I get 18.98 milliliters. Again, we're going to go back and look at significant figures. Since we're doing addition subtraction, we're going to carry down 2 decimal places. So we're going to have 2 decimal places in our final answer. There are different types of titrations you can do. In this experiment, we'll be looking at an acid-base titration. When you react an acid and a base, your products are salt and water. This is also called a neutralization reaction. A common example is the reaction between hydrochloric acid and sodium hydroxide. When they react, it forms the products of sodium chloride and water. In lab this week, we'll be looking at the reaction between citric acid and sodium hydroxide. In order to measure the progress of this reaction, we'll be looking at the pH. Because this is a neutralization reaction, we will know when the reaction is complete based on the information collected about the pH. We'll use a beaker to collect our liquid. We'll have our burette set up on a ring stand with the burette clamp. We'll clamp the drop counter to the ring stand and rest the pH probe in its holder so the meter won't bump the bottom of the beaker. It's okay to attach the clamp for the pH meter and drop counter to the same ring stand as the burette clamp. The drop counter is used to help MeasureNet to keep track of how much volume you've added to the beaker. This is an example of what you'd see for an acid-base titration, such as the one we're doing today in lab. The drops, as indicated by the circles, start at a pH of approximately 4. It increases slowly until it reaches the near equivalence point. Then it increases rapidly. It finishes at a pH of almost 12. At this point, we have far more base in solution than acid, whereas at the beginning of the reaction, we had more acid than base. What we want to find out from this graph is the equivalence point. The equivalence point is the point in which the moles of H plus equals the moles of OH minus. This doesn't necessarily mean that the moles of acid equal the moles of base. That depends on the formula of the acid and base. The moles of H plus equals the moles of hydroxide. The Y versus X plot here shows you the actual curve of your titration. This second plot is actually the second derivative curve. For those of you who've had calculus, you're probably familiar with the term second derivative. For those of you who haven't, that's okay. We're just using the second derivative as a means of helping you identify the equivalence point. When you look at the second derivative curve, you look at the point where the value on the second derivative curves goes from positive to negative, as indicated by the highest dot and the lowest dot. We're going to trace across here, and we'll see that the line crosses the 0 point. That's where I'm going to draw this X, where it crosses the 0, and that's our equivalence point. We look at the volume based on the data in the graph, and we see at what volume we're at this point, and that's going to be where our equivalence point is. Now we know the equivalence point and how much of our unknown solution we used in the beaker, and we know the concentration and the volume of the known solution we used. Now we need to find the concentration of the unknown. That's the whole point of doing a titration. To do that, we look at the stoichiometry. This is going to be a lot like the other stoichiometry problems you've done. The big difference between this stoichiometry problem and the others you've done is that you looked at the amount of reactant and looked at how much product you're forming. In this case, we're going to be comparing the two reactants. For stoichiometry problems, it doesn't matter whether you're looking at two reactants, two products, or a reactant and a product, as long as you start from a balanced chemical reaction. I'll work through an example calculation in another video, but in our next video, I'll walk you a bit through the experiment we'll be doing in lab. Remember, if you have any questions, please speak with the TA in the General Chemistry Learning Center prior to going to lab, as they are there to assist you.